I've designed 4 different sections. We will do performance optimization with NumPy and Numba in the morning, this first section. Then we will see how to link to C++ code. Yesterday you have programmed in C++, and this is another important aspect of Python. And for this we will use CPP-UY. In the afternoon, we will see how to use Python, MPI in Python. So we will apply some of the exercises that you did yesterday. And we will conclude with some example on actually how to use GPUs, because the machine you have access to, Cyclone, is also a GPU machine. And most of the HPC systems nowadays are going with GPUs. So it's important also to have an idea on how to use GPUs on Python. Okay. Then this is the program for today. We will finish slightly earlier than yesterday, because then at 4 there is a seminar that you should have all received information about. It's anyway on our program online. And then if you want to follow it, you're very welcome to join. It will be quite interesting. It will be about astrophysics from Professor Andreas Efstatiou from the European University. So, okay. So before starting, why Python? From my side, it's a language that I really like, and I'm really enjoying on using it in HPC, especially. So this is a quite a new approach for Python. It has seen a huge growth in the recent year, and at the moment is the most used programming language in data science. And this is mostly due to its to the frameworks they've implemented for machine learning, and also for some very user-friendly applications like NumPy and other modules for analyzing data. So for this reason, it's quite used by all the community and from entry-level users. And on the other hand, it's a programming language that is based on its growth. It's not the fact that people have been able to deploy such powerful modules is also thanks to its original structure that was very well designed, and it's an interpreted programming language, it's user-friendly, and what has been well designed, it's how one can easily deploy software. So I've personally deployed several packages on PyPy, and it's very easy to do it. So if tomorrow you want to design your own package and share it with your collaboration, you can easily do it on this here on PyPy. I will show you in a second. And on the other hand, it's also built somehow on a scientific approach via the usage of PEPs. So the PAPs are Python Enhancement Proposals. Okay, let's open in a second these 2 links. So PyPy is where basically all the modules are distributed. So for instance, if you look for NumPy, it's going to be distributed here. And this is the latest version, and you see various released. And so when you just type pip install NumPy, pip is going to look on PyPy for this module. And basically, if you register and you have your own account and you create a package that has a unique name, you can also distribute it on this website. Okay, no, it's not that you have to do it. You will then easily fill up this fantastic repository with a lot of packages people may not use, but it is done by others. So if you plan to maybe distribute something, you can try to do it like this. And the same way the PEPs are these Python enhancement proposal. Like I said, they are built somehow on a scientific approach, because anybody can write a kind of paper and proposing a change to the programming language. So this is done here by several people, and here you can see practically how the programming language has changed over the year. So here you see the new PEPs that have been submitted. These are the ones that have been accepted in the past, others that are open, other rejected, and these are basically all the changes that Python has, or the main changes that Python has seen during the year. So they are here. Basically, if you open any of these, you will see that is a kind of proposal where there is an introduction, proposal on the change, etc. So it's a very nice programming language. On the other hand, it's not meant for HPC by its own. So it's not like other programming languages like Julia or others that you see here, C, C++, that are really meant for HPC. So there are some performance issues that can easily be overcome. And the main source of these performance issues are mostly due to the fact that Python is an interpreted programming language. So interpreted, it's always in all the programming language equivalent to a bad computational performance. And this is due to the fact that one is adding a significant overhead to all the instruction one is submitting. So you have some source code that is given to a parser that translates it in a pseudo code that is named bytecode in Python. Then you have an interpreter that reads this bytecode, it processes it instruction per instruction and produces the results. During this process, it may use some compile libraries, and this is what, for instance, NumPy is doing, but it's not the same as you will do in a compiled application where you have a library, an optimized library, you compile your application, and basically you just cut short all the rest, all the interpreted part, and you put all the instruction together in order to go from the compiled libraries to the result without having to add the overhead of the interpreter. Though on the other hand, it's like, I know it's the fact that it's said interpreter is the main reason why everybody is using it. It's fantastic to be able to write the code and directly test it. Just the suggestion when you use it in HPC, never do for loops on data. This is the major point. So now this is the end of the slides I wanted to show, and now we go on the notebook. The notebook, the main notebook now, it's pretty empty, but we will fill it up during the day. So I've prepared some things to show you. I will type them in because I think it's more useful for you if you follow me instruction by instruction and you can interrupt. So I give you time also for interruptions and ask questions. So the topic is Python for HPC, and let's start from a summary of the beginner training, where the main purpose of the beginner training was twofold. On one side, to show you that pure Python is slow, and on the other, to show you how to use multi-threading in Python. So that I give it per granted. Just let's see a summary on this. Basically, at the beginner training, I started with this example where I showed few examples, and I asked also people to try to give me others on how you can add two arrays. So let's take x1 and x2 that are two arrays of the same dimension, and you basically want to sum them up, the component by component, so element-wise, in order to create a second array. So our first approach was like this. I create a list, I loop over the x1, and I append the instructions and I access element by element, and I do the sum and append them to y. So this was a first example. A second example was, so basically here we are looping. This is what you will practically do in C, where you write a for loop over the size of the array and you access the elements. This in Python is slow because you are doing two operations. One is the loop, and then you are explicitly accessing the components. Some overheads can be cut if you loop directly on the content of the array. And this you can do it with the zip function that is zipping together the two values, the value by value of the array, returning two single values that are the value at the position I. So we are zipping together these two arrays like you will do with the zip of your genes. So you are zipping together the two sides of the array, and you are getting element by element, and then we are summing them up. So this is the same of the function above. And this is faster because Python is doing for us the element access. So we are saving one instruction. But it's still slow because we are constructing dynamically the array. So we started from an empty list and we are adding instruction by instruction elements. And so this actually at the C level requires resizing the list or using pointer to pointer, or expanding the list with other elements, but requires this a dynamic append of the components to this list. And for this reason is significantly slow in Python. The best you can achieve in Python, it's I think what it's written here in add 3, where basically we are zipping the values, we are adding them together, and we are use an automatic generator for the list of Python that will understand the size of the list and generate it for us. So we are not actively append it, but here basically, if I suppose you know this kind of instruction, this is the list, and instead of saying the components of the list, like you will do in a standard list, you will say 1, 2, 3. Instead of explicitly saying the component of the list, you are saying that the elements for I in range 3. And this is equivalent to saying 0, 1, 2, 0, 1, 2 in this case. So, sorry for I said it, but not read. So this is equivalent. So basically, we are dynamically generating the list. And this is, I think, the fastest you can achieve with pure Python. Then, of course, since X1 and X2 are going to be, I suppose, they're going to be NumPy array, what you can simply do is to use the NumPy. Sorry, someone changed the thing. Don't know. I overwrite it. Don't change this notebook. Otherwise, we'll receive that. Yeah, follow me please from the screen. Don't follow me from the notebook. Follow me from the screen. So yes, if you add X1, so if you add their NumPy array, you can use directly the NumPy built-in, and you will add them like this. This is significantly faster. Now we are going to see how much. So I run this cell, and then here you can also run them from your extent. That should not be a problem. Here, what you can do is what I'm going to use now is just to use from Pandas the data frame for easily drawing the graph, so I don't have to directly draw the graph. And what I'm using here now for testing the timing, this I will do it also after on, is to create a list of index where I'm going to run on. So these are index, again, I've generated dynamical list. These are going to be the powers of 2, from 2 to the 0 to 2 to the 11. Okay, so these are going to be these kind of sizes, suppose, right? So it's 2 to the power I. These are going to be the index, the x-axis of my plot. And what I'm going to do then is I create the data frame of Pandas with these indexes. So if you don't know about Pandas, you can, yeah, maybe then have a look. I will not go into details about this now. And this is a data frame, so it's going to be a table, basically, the times. And then I'm going to assign at a position size and at a name, the name of the function, the time of the function. So this is what I'm doing in this example. And if I run it, you can see that add 1, 2, and 3 are getting faster in time. So these are 1,000 applications of it, and this is the time they take in second. These are getting faster, but if you want to see how fast is actually NumPy, this is going to come up soon here. And if we want to see how fast is NumPy, well, NumPy is this fast. You don't see that, I mean, it's at this scale, it's not compatible. It's 0, looks like to be 0. It's not 0. We can plot, we can put logarithm axis. So I can say log on the y-axis, so log y equal true. So this is why I'm using Panda in this way. So I can, this is log y equal true. So you can see that on the y-axis, we are how many? 3 order of magnitudes faster with NumPy with respect to Python. Let me put also, to avoid this effect, because I'm increasing exponentially the x, let me put also log x equal true. And now we are going at power of 2s, and basically it's this. It's flat, then starts growing. Okay. Just a comment before asking for questions. Why this one is increasing linearly while this one is flat and then starts growing? Can someone... maybe, yeah, the point is, if you have an idea, the reason why is that is flat here, this is named overhead. So what you see here is actually the overhead that is required to starting the extraction of NumPy. But then, so this is a constant cost that you have. And this constant cost is much greater than the cost of performing, of performing the operation. So you see that here starts to increase linearly. If you extrapolate this linear increasement to the beginning, you see that actually doing the operation here costs nothing, and what you're paying are the overheads. Then at some point, the overheads are constant and are taken over by the cost by NumPy. So NumPy is then starting to grow linearly here. Okay, so NumPy will grow linearly, and I can show you this just maybe to speed it up a bit. We comment out the others, and I go to the power 15, and you see that if I plot it again logarithmic scale, this is flat and then starts growing linearly. So this is the region where you are actually seeing the cost. This is the size of the array where you completely overcame the overhead. Up to here, you are seeing the overheads. So these are overheads due to Python, but similar overheads you would have also in C, C++, I mean, whatever other language you're using, because there are still overheads when every time you want to instantiate an instructions are very small. We did 1,000 operations, and you see that these overheads are of the order of milliseconds for 1,000 operations, so are the order for one operation of the order of microseconds, so are very, very small. But the cost of adding two numbers is much smaller than that. Okay. Questions? If there are questions, please ask now. Otherwise, I proceed.
I have a question, which might probably be a bit stupid, but
no, don't worry about stupid questions.
If you the slow examples with the for loops,
yeah,
we started with the output array list. Y is its length is not pre-allocated. Would that make any difference if we had made it, a larger, if we had allocated space for that?
Of course. Yeah, of course it will make a difference. Though Python, it's not like other languages. Yeah. For instance, in C++, you could do that. When you create an array, a dynamic list, you can pre-allocate it. So say the minimal size that it is going to have. In Python, you cannot do that. You can maybe instantiate it with zeros. So you can say 0 times len of x1. I tried, but even if I do this, suppose, and so then I do not do append, but I say, this is a very good question actually, y of I equal this. So this is a way of pre-allocating the list, right?
Yeah.
So I fill it up of zeros, dynamic directly, and then I just allocate. This, let's name it, I copy it, I go back, let's add it here. Let's name it 1, 2, and let's see how faster we go. So I remove, I uncomment these parts, I comment this one, and I say add 1, 2. So I remember when I was preparing these examples, I tried this, and it should be faster, but it's not as fast as the dynamic allocation here. So you still have an overhead because you're looping over the data. Why is it taking so much time?
Because you left the 15, you run it 15.
Oh, thank you a lot. Yeah, you see, perfect. So let's put 11 now, and it should be faster. Yeah, thank you. Yeah, we will never finish otherwise. So the add 1, 2 is slightly faster, but neither as fast as when I'm zipping. So it's still. Yeah, I don't know. Maybe if I apply it here now, okay, we can try it more. You can try it afterwards. If you apply it here, maybe you can get as fast, maybe as add 3, but it's on the limit if you zip it as well. But thank you for your question. So though it should be clear that Python itself is slow, and this is something you should never do. Never try to optimize Python alone, okay? Okay, so if there are no other questions, I will proceed. By the way, okay, there is, you can always raise your hand. I have on another screen the chat, so I may not see it immediately, but interrupt me when I'm talking or raise your hand. I will check for it, or write on Slack, and maybe someone else can reply to you. I have everything open, just it's on another screen, so my focus is here, and I might not see it. So, okay, this is beautiful, and NumPy is working very well, and it offers you a lot of good tools. But if we want to do something more complicated, because that's what practically you have to do in your day life of research, you don't want to just simply add vectors, but you suppose you want to do something a bit more complicated. How do we, I took as an example for today the Laplace operator, and the question is, how are we going to optimize such an operation? So just a summary on what is this Laplace operator. If there are physicists between you, or maybe some of you have some fresh knowledge of, I don't know, physics 1, where you see some wave propagation. The Laplace operator, it's this operator here, the Laplacian, which is basically the derivative squared, and it's the derivative square, the sum of the derivative square of a function over all its directions. Okay, this usually it's used for describing the propagation of waves, and you can, from it, for instance, you can define a Poisson equation that describes how wave propagate on a mean. But okay, this is not the focus. The background of the Laplace operator is not the focus of it. It's just something that if some of you is doing fluid dynamics or other kind of physical problems where you have derivatives, you may encounter this operator. A way to study this operator numerically is by discretizing the space. So you discretize the space with a separation h, which should be small, and then basically your square derivative becomes this operation here. So I'm taking the difference of the function taken at a place before, at a place after on x, at a place before, at a place after on y, minus 4 times in the middle. Okay, so this is a symmetric approach on discretizing the second derivative. So yeah, I don't know if you have questions on this, but yeah, it's not really the topic of it. Just the point is how to implement this kind of function efficiently. Okay. A way to do it, we can do it numerically. So let's, okay, let me copy and paste and I go line by line. Let's take an array now. Let's use NumPy, but just NumPy, it offers you some tools for doing that. We will see it after. But as first, let's suppose you are not aware of the full functionality of NumPy. And so let's suppose your only idea of doing this operation is actually doing it in pure Python. So on looping over the directions. So if I can loop over X and Y. So what I'm doing here, I have an input array which shape is size 2. So I'm supposing that it's something that has dimension X and Y, like this one here. So it's our function here. Our output, well, it's going to have the same shape of it. So I instantiate it as a 0-like of the array. And then I'm going to fill it up. So this I'm instantiating a copy of the array. And then what I'm going to do, I'm going to loop over its shape. So capital X, capital Y are the dimension of the array. And what I'm going to do is to check how I'm going to assign to the value of this array the value of the function at the separation. I fix age to be 1, and at the separation -1, +1, -1, +1, X and Y. Now, why did I add this instruction here? Well, this instruction here, I added it for the simple reason that NumPy by default, if I create an array, suppose I create so let me put a range of size 10. Let's suppose I do this. A range of size 10. If I try to access the component -1, so let's take that X is equal 0, then this is going to be the component -1. R of -1, it's a valid, and it's the other end of the array. right? So NumPy, when I go negative, it's automatically looping behind. But if now I do, I'm at position 10 and I want to do +1 like I'm doing here, if I try to access the position 11, what will happen? Well, it will tell us, which will give us an error and telling us the bound, index 11 is out of bounds for the axis 0, which has size 10. So you're trying to go over it. Yeah, okay, so NumPy is well defined when I'm doing, when I'm trying to wrap the array on the left side, so -1, but if I try to go over the array on the right side, even if I try to access component 10, because this is index from 0 to 9, I cannot do it. And so the way to do it numerically is to say, well, I put a module 10, which is the size of the array, and then I'm starting back from the beginning. So now I got 0. And if I have 11 module 10, I get 1, and 12, etc. And suppose I do 22, it's still well defined. Okay, so this is the reason why we have the module to wrap around. All right. So this is a way to implement the Laplace operator. It's one-to-one with what is written here. There is a factor of 4, age has been fixed to 1, so we don't divide by 1 square. Questions? Okay. Then, so yeah, there are no hands up, so yes. So now, before going on the numerical part, let's just give you a nice example of where this Laplacian operator is used. Like I told you, it's used in for describing the propagation of waves, but it's also used, for instance, in some image processing. And so let's see an example of its application. And for instance, I'm going to apply it for some of an image. So this is an example I found online. So suppose we take the, this is another package, sky image, and I don't know if, yeah, I import, it is a package that has several images in it. So inside this data, you can find several images. This is, for instance, the image of an astronaut. But if I do dir of this, you can see that there are many others. Okay. And basically, I'm getting this astronaut, and this is an image of shape. The image is something that has shape 512, 512, which are the X and Y axes. And then 3 are the component, are the color, the RGB components of the image. So we can simply see this image with from using PyPlot. So we can depict it, and if I say plt dot sorry, a second, someone on Skype. Sorry, someone wanted to join in the, anyway, sorry, yeah, I can depict the image using PLT with image show, and if I say image, you can see here the image we're going to analyze. Okay, this is the image of an astronaut, like you would deduce before. So now, here we have 3 numbers. This is a problem at the moment for what we want to do. So let's make this image black and white. So I save the image as color, and with this function of image of sky image that is RGB to gray, so this is going to make it in a black and white scale, I can get an image which size is now only 512 times 512. By the way, I did it twice, just a second. Which size is 512 times 512. And now is something useful for applying our Laplace operator, because we have only 2 axes, X and Y. Okay. Just for the future also, I will define a function like this that is comparing 2 images left and right. Okay, so this is creating a subplot of dimension 2, and I'm going to compare the images. And what I'm going to do is to compare these 2 images that I created, color and image, And you see, this is our black and white image. So I'm saying to use a color map that is gray, and this is the image gray, but you can use any other color map for now, since it's only this one number. And for instance, I don't know, I can say there should be something that is blue, white, red, and now this image is on a scale blue, white, red. Okay, but let's keep things simple, and let's go with the grayscale. So this is our image, and an application of the Laplace operator now is to, for instance, use in images for edge detection. So let's see how this applies in our case. So what I can say edges of this image is equal to the Laplace operator of image. And if I compare the value with adding also an absolute value, so I compare this Laplace operator of the image with an absolute value, what you see, okay, now it's maybe hard to see, I don't know if you see all the details, but if you roll, now I save the notebook, you can reload it and see by your own, you should be able to see that now, okay, my contrast is not very good, I don't know if yours is better. You should see that we can detect the edges of this image here. Do you see it? Do you like it? So this is an application of this approach, for instance.
Yes, we see. Yeah, not very well, but we see.
Perfect. So yeah, I have it on my other screen. I see it better. So if you try to reload the notebook, like here, I saved it now. So if you reload notebook from disk, you should maybe on your screen see it better. Now, other questions. So this was just an application, but an example, motivation for you, why this Laplace operator is used. In another example, it's a simple one. It was mostly an exercise. We are 10 minutes away, so okay, we lit 10 minutes, like I said before, but let's go ahead and give you a first exercise. Then we discuss it maybe at the end of the break. Maybe let's do that. Okay, let's do this after. So here we have our operator, the Laplace operator that I've written here. This is applied to an image. The same operator is also found in, for instance, it's something that is applied that is common to use in image processing, like I told you. And for instance, you can also have it under SciPy. So SciPy itself, it has this operator that is ND image, and sorry, under ND image package of SciPy, you find the Laplace operator. And if we use it, you see that, sorry, why image is not defined? What happened now to my notebook? Why did it restart? It restarted for some reason. Maybe something happened. It may fail. Okay, let me redefine everything like this, and then now I should be able to run it. No, compare is not defined still. Sorry for the delay. Okay, you see that we have the same behavior here, somehow similar behavior, up and down. Actually, it's the same. Okay, so this is the Laplace operator image. Now, if we want to check that it is actually the same, what can we do? Well, so this is what is implemented in Laplace. This is what we want here, and let's try to check what if it's actually the same. So let's define a random array. The best to do when you want to check if something is the same is to define a random array. So let's define a random array like this one here. And then let's check if our Laplace, that I don't know if I already defined, if our Laplace here is the same of the one of ND image. What do we get? We get false. Why do we get false? So for this is we are checking if our Laplace operator is the same, and it's not. Why it's not the same? Well, let's have a better look. It looks the same in the application, but it's not the same. Now let's have a better look to the to the documentation of it, you can either look at the documentation of it using help of ND image Laplace. And you can see that here, okay, this is a documentation. Now we go through it. Or I put you also here a link online if you prefer to check it online. So if we read about this, well, this Laplace operator takes as an input, an output, and then a mode. Which mode that the default value is reflect. So what is this mode now? This mode is how how our function behaves at the boundaries. So the default value for our function at the boundaries is to reflect. Reflecting means that when we are at the boundary, we are doing -1. We don't wrap around, but actually we take the +1. Okay, so this is what by default the Laplace operator is doing. We don't see any effect here on the boundary because, okay, there is not so much different because it's 1 wrong out of 4, so we don't see big effects. But if we go to compare, we see that this is where the problem lies on. Of course, it implements also other constant, nearest, mirror, wrap, and wrap is actually what we are using. So mirror will use the same value, nearest will use the closest, constant will put a constant, and you can give the value of the constant in cval, or wrapping, it's wrapping around. So if here I add mode equal wrap, then the result is true. So they do the same job when Laplace is wrapping. So Laplace is doing actually more than what we ask for, more than our own function. And it's also doing more under another aspect, which aspect is it's said by this, the fact that it is under ND image, where ND means n dimension. So this is the same point of MPI array. These are n-dimensional array, which means that it works for n dimension of the array. So if I do now ND image Laplace, and instead of an array of dimension 2 by 2, I do an array of dimension, an array of dimension 2, I do an array of dimension 3, this still works, okay, will give us a result. Maybe I shouldn't have printed that. It still works, so I can say dot shape. It still returns this result. Our function doesn't do that. So this Laplace operator is better under 2 aspects: the fact that supports a mode, the fact that supports an n-dimensional array, and under the aspect that is faster. So I can do it, I can go here. So that's, for instance, a reason why to use that one and not what we implemented. So if I go in performance, if I try to analyze the performance, I see that if I compare this ND image Laplace with the Laplace itself, so I do the same way that I did before, range up to 12, Laplace operator of the image, our Python operator of Laplace. I run it only once because it is a much more expensive operation. I plot in logarithmic scale, I run it, and I see that, okay, it's taking also a while because of our Laplace, but we should see very soon that, well, SciPy is faster. Again, some order of magnitude faster. So these also tell us that SciPy is not using pure Python, but it's using something that is compiled. Okay. So now I would like to, we're very close to the break. I think this was already enough content. I mean, I wanted to do more in this morning. I wanted to arrive already to Numba, but I believe it's better if we actually, okay, maybe give up something or I make something else shorter. And now I would like really to give you time for exercise. So maybe I will explain now the exercise, then let's start the break. Let's say 25 minutes of break, and we start with 5 minutes earlier, with some of you showing me the result of the exercise I'm going to give you. So I really would like some of you to to give me to try it out now. So okay, if you want to take a break and not do it, it's fine, but try out things in your notebooks. I hope these will support I mean the node. I've dedicated a full node, so it should work, it should support all your computational demand, but try out if it crashes, okay, we will try after some other options. But now I would like all of you to try out some either what I wrote here, some exercises, or if you really want to do a break, take also a break. And I'm going to give you now the exercises. So I will give you the exercise number 1. So the exercise number 1 is to, sorry, let me copy. The exercise number 1 is to implement other modes of Laplace, like reflect, constants, nearest or mirror. So choose what you want. It's not, you don't have to implement all of them, but just to try it out in our function we have above. So in the function, let me copy and paste here. So to edit this function that is here in order to support other modes. Okay, so this is the first exercise. So instead of wrapping like we're doing here, try to implement other modes at the border. And then I would like to see some results there. And exercise number 2, choose the exercise. If you find, if you're expert Python users and you find the first 2 simple, maybe try then others. It's you don't have to do all of them. I mean, if you want to be challenged, try. These should be of increased difficulty, not really. Okay. Next exercise number 2 is to make the Laplace function that is above still valid for an n-dimensional array. So this is limited for a shape of 2 dimensions. Try to find a way using pure Python to make it valid for an n-dimensional array. Okay. And an exercise number 3 that I have here, like I said, choose the one you like more. Sorry. And exercise number 3 is to write the Laplace using the numpy.roll function. So using numpy instructions, in the case numpy.roll, that you can read the documentation by just, for instance, here doing np.roll. Here it's an example. I put here an example. So I saved the notebook now. I'm open for questions, and you can start working on these exercises. And if someone had problems on connecting, we can try to resolve. Maybe I don't know if I should. Yeah, okay. Yeah, let's go ahead and you can start the break once. Try out the exercise. If you have questions about exercise, connecting, etc., please ask now.
Thanks, Simone. I'll stop the recording for now and start again later. So we begin again in 25 minutes, you said, yeah?
Yeah, I will start from seeing some solutions to this exercise, then give mine, and then we continue. Yeah, thank you.
Okay, thank you.